Alright, welcome back to Physics 11. So today I wanted to start talking about the application of forces. So in the channel named Dynamics and Application of Forces, I already posted the answer to the quiz that you did before the break, and I also posted the notes packages. So this is what we did before the break, and you can find all the answer keys and all the solutions in the class notes section. And this is the new section which we're going to be starting today. So what I've done is I made a video which relates to the section 5.1 in this notes package. So let's take a look at the notes. So force of gravity. Now this was done by Isaac Newton. So he was the one who discovered this relationship, and the reason it's called the universal gravitational law is because it applies to any two masses. So gravity is an attractive force between any two objects, whether they're close together or far apart, doesn't matter. There's always going to be a force acting between them. So again, this will depend on their masses and their distance apart. So the equation itself is given by the following. We have the force of gravity, Fg, equal to the capital G, which is the universal gravitational constant, times the capital M, which is the mass of the first object, and lowercase m, which is the mass of the second object. So again, the universal gravitational constant has a value of 6.67 times 10 to negative 11 newtons times meters squared divided by kilograms squared. And the two m's are the masses of the objects. Now a lot of times you can see this equation where the m is just written as m1 and m2 rather than capital M and lowercase m. Now the r value is actually a vector value. That's the displacement. That's why, again, we end up with a force which is also a vector. So again, r is the distance between the centers of mass of the two objects. So let's take a look at the first example. So this question says, what is the force of gravity exerted on a 70 kilogram astronaut that is standing on Earth's surface? So here is the radius of Earth, which means that we have our Earth. Here's the center. Here's the R value, 6.38 times 10 to the 6th meters. And here's the person standing on the surface. Of course, we have two masses, lowercase m, capital M is going to be the mass of the Earth. So all we have to do is write the equation Fg equal to the gravitational constant times capital M times lowercase m over r squared. All right. Don't forget to square the r. That's a very common mistake. People forget squaring that. I forget sometimes too. So, of course, you'll get the wrong answer if you don't square it. So the g value is, again, is on your formula sheet, so you can refer back to that. Okay, our capital M is 5.98. Again, this is also on your formula sheet. 24. And the mass of the person is 70 kilograms. This over the radius, 6.38 times 10 to the 6th squared. All right, so when you do the calculation here, you will get a value of 686 newtons. So that would be the attractive force of the person standing on the surface of the Earth. I think if you think back to the time before the break, we learned about this force of gravity equation, which is just m times g. Well, let's see what happens if we do the same type of calculation with this equation. Well, m here is going to represent the mass of the astronaut. So I'm going to plug in our 70 times 9.8, and we also get the same answer. So why is that? Well, this equation is a special case of this equation right here. So this is the universal gravitational law, which applies to any two masses. The equation we saw before the break only applies to the Earth, and it only applies to the surface of the Earth. So if you think of this equation, all of this is your little g, which leaves us with the lowercase m, same as here. So if you take all this together, you'll get 9.8. That's why we can use either one whenever you're trying to find the force of gravity or the weight on the surface of the Earth. But if you want to find the force of gravity, or rather the force of attraction between any two objects anywhere else, you have to use the full equation, which is the capital G times the two masses divided by r squared. So let's take a look at the second example. Now in this case, we have the same astronaut, but in this case, the person is at an altitude of 6.38 times 10 to the 6 meters, which is again the radius of the Earth. So the altitude here means that the distance is about the surface of the Earth. So if you look at the diagram for this case, this is going to be twice the distance away. So there'd be somewhere here, right? So twice the radius. So this would be your r, and this would be another r because the values are exactly the same. So overall, we're going to get distance of 2r here, right? So again, this was the value for r in the first example. So the further away, the smaller the force should be, right? Because if you far enough from the surface of the Earth, you will actually experience zero gravity. You'll be able to float. So we should be expecting a lower value than in the first example. So let's see what we get. Now I'm going to write M1 and M2. In this case, it's just easier to label them this way rather than using capital M, lowercase m. But again, like I said, you can find them in both forms. So, M1, let's make it the mass of the Earth. So again, this is the same number that we used in the previous question. And M2 is going to be the mass of the astronaut. So the only difference here is going to be the value for r. That's going to be double. So let's plug in our numbers. So 6.67 times 10 to negative 11, 5.98 times 10 to 24, and times 70. Over 2r, right? So what we're going to do is plug in either 6.38 times 2, or you can just add them together. Doesn't matter how you do it. You're going to end up with 1.276 times 10 to the 7th squared. Now in this case, once you do the calculations, you're going to get 171 newtons. So, as expected, the value is smaller. Now notice that if you were to use the equation Fg m times g, this is no longer not going to work, because here we need to know that value, which we can't get unless you actually go up twice the radius of the Earth and measure it at that point. So this one, not going to work. Again, this is only for the surface of Earth. Anything above or below the surface of Earth, you have to use the full equation. Okay, let's take a look at the third example. Now, in this case, we're not talking about the Earth, we're just talking about two people sitting side by side. So it says here, one student has a mass of 55 kilograms, the other one has a mass of 65. If they sit half a meter apart, or 50 centimeters, what is the irresistible force of attraction between them? Okay, so first, notice we need to convert this to meters. So let's say my M1 is going to be 55, M2 is going to be 65. My distance is 50 centimeters, 50.0, or 0.5 meters. So remember, we had to use meters here. Okay, and what else you can write here? Capital G, in case you forget, is 6.67 times 10 to negative 11 newtons meters squared over kilograms squared. Now notice the meters squared and kilograms squared will cancel away once you have your mass times mass divided by r squared. So that's why you're left with force, which is just newtons. Okay, let's plug in the numbers. So we get 6.67 times 55 times 65 divided by 0.500 squared. Okay, now this equals to 9.5 times 10 to negative 7 newtons. So again, very tiny force here. So this just goes to show you that on a microscopic scale, the force of attraction between two masses, two people, two cars, whatever, is going to be very small because the masses had to be really, really big to actually make a difference. This is so small, it's basically negligible. All right, so the last two questions are not necessarily just plugging in numbers. The last two questions that I have here are more about logical thinking and really knowing your algebra. So here's a typical problem that you might encounter. So the question says, astronaut weighs 800 newtons on planet X. How much would she weigh if she was at an altitude equal to the radius of planet X? So notice we don't have any values for the planet X. No radius, no masses. All we know is that on the surface of it, the person weighs 800 newtons. That's all we do know. So what we're going to do is take your equation, Fg okay, times m1 times m2 over r squared. And we know that this is equal to 800 newtons. Now, the next part says here that the person is at an altitude equal to the radius. So basically, we double in the radius. So this would be at the surface, so let's call this Fg1. And let's write the equation for Fg2, where we're going to double the radius. So if you're going to double the radius, means you're going to do r times 2. So again, the equation is going to be very similar. The only difference now is that instead of just r, it's going to be 2r squared. Now let's pull this 2 to the front of the equation. So we're going to use our exponent laws here to move the 2 outside of the parentheses. So 2 squared is 4. So that's what we get. And then, if you look here, the expression from Fg1 is the same as this part right here, right? So the only difference now is that we have this quarter factor in front. So we can also rewrite it this way. 1/4 times Gm1 m2 over r squared, right? So this is exactly the same as that. So this part here, we know that this equals to 800 newtons from the first equation. So all we have to do is really just replace this with 800 and divide it by 4. That's what we're going to do. We're going to take our quarter times 800 newtons, and we're going to get 200. So at an altitude twice the radius of planet X, the person is going to weigh 200 newtons. So notice we did not plug in any numbers for m1 or m2 or r. Right? We don't know what those values are. We just know that the distance was twice the radius. We just doubled the r value, that's all. We're still able to find the answer. So here's another very similar type of problem. So this one says a spaceship orbits the planet at radius r and weighs 1,000 newtons. How much would it weigh if the orbit of the planet was twice as massive and half the radius? So the mass is going to be twice as much and the radius is going to be half the distance. So let's do the same thing as before. Here's what we know. First of all, Fg1 is going to be Rg m1 m2 over r squared equal to 10,000 newtons. Okay? So again, we don't know what these values are. In Fg2, we're going to apply the last part of this question. So we know we have to double the mass and half the radius. So let's pick one of the masses, doesn't matter which one, m1 or m2. Let's say we take the first one, m1, and double it. Okay, that will make the m2 our spaceship. m2, sorry. And then for the radius, we're going to multiply it by half or divide it by 2. So 1/2 r, and then square the whole thing. All right, so we're going to do the same thing as before. We're going to pull these coefficients to the front. So 42 is pretty easy, just right in front. For the radius, we need to square this. So 1/2 squared is 1/4. So we get 1/4 r squared. Okay? So again, we end up with g times m1 times m2 over r squared. Same thing here. We get this is the same as that. Right? These are exactly the same. So the goal, again, same thing. Plug in the 10,000 newtons for what we do know and get the value for Fg2. Before we do that, we can also simplify this coefficient that we have here. So right now we have this 2 over 1/4. So this is the same as 2 times 4 over 1, which is going to be 8. So we can actually rewrite this as 8 times g m1 m2 over r squared. So then all we have to do is just replace this with 10,000 and we'll get 80,000 newtons, which means that if you're closer to the planet and the planet is much heavier, twice the mass, of course the force is going to be much bigger. In this case, we end up with 8 times the value. Okay, so notice these last two questions, they require some logic, right? Not just plugging in numbers. So make sure you read the questions carefully. So the practice questions that go with this are, again, in the notes package, and it's labeled Worksheet 5.1, Newton's Law of Universal Gravitation. So there are 11 questions. The answer key is at the bottom. Eventually, I'll post the answer key to that as well.